Thank you, everyone. What the heck is that all about? So just trivia fact I was asked about in the green room backstage. Where was I born? Transylvania. Name sounds Italian. Now we got to Latin vampire. We're in an era right now where even 6 months ago, if you'd have told me about the models we have right now, I wouldn't have believed you. The models have gone from GPT, generative pre-training, to reasoning models. And so much so now that, we don't even call today's models LLMs anymore. We either refer to models as non-reasoning models, what we used to call them just 6 months ago, or reasoning models today. So the prior generation of models were in an S-curve, a long S-curve, about 6-7 years, starting from the infamous "Attention is all we need" white paper, back at that NeurIPS conference in Montreal, where I'm from, by the way. And through the rapid evolution and maturity of all the cool non-reasoning models. And now, I can't believe we're already pretty much halfway through 2025. I can't believe we're pretty much halfway through this decade. It's been a memorable one. And reasoning models have really accomplished the impossible if you just take a little step back and look at their power, their capability, their intelligence. The ARC Prize used to be a benchmark created by Francois Chollet and a few other researchers that was meant to never be defeated, never be reached by the non-reasoning models. And yet Sam Altman and his crew of researchers last December during the 12 days of OpenAI Xmas kind of did their one more thing Steve Jobs moment and dropped a preview of O3 and defeated the ARC Prize. But the question is, at what cost? At what cost is this amazing scale available to us right now? Let's answer that. We're seeing that the GPUs are melting right now, right? Any viral app literally runs into rate limits, into capacity limits, into some hallucinations and really, really poor latency. And we need to fix that. And fortunately, our friends in Guangzhou, if you know where Highflyer is, a parent company of DeepSeek, have been prolific in publishing best practices, open source best practices about exactly how to solve this problem. So everyone knows DeepSeek and R1, and maybe if you know anything about their history, you know about their V2.5 and V3 models. Very few companies, even Meta with Llama 4, Llama 3, on the open source side, haven't disclosed the details of their infrastructure and infrastructure operations. DeepSeek has. It's another one of the many reasons why they're so widely respected in the community. What you're looking at here is how they do what used to be thought the impossible. They combine training and inference on the same GPUs, on the same nodes in the same cluster. Usually these are dedicated things, very far apart, sometimes with explicit or implicit firewalls in between them, between the researchers and the operators. DeepSeek said, nah, we can't do this. We can't afford to do this. We have to be way more efficient with our export control resource constraints. And so what they do is they do inference and they bring in the revenue throughout the day, and then overnight, they elastically do just-in-time training. And as demand picks up again in the morning, they elastically and dynamically switch. And this is incredibly hard to do with GPUs and tens and hundreds of gigabytes of data moving in and out of memory all the time. They elastically ramp up inference and elastically, dynamically tune down training. And that way they don't need 2 or 3 clusters for the same thing. They do it all in one. Remarkable. If you take a look back at some of their earlier publishings before the recent open source disclosures, DeepSeek have been publishing really cool research for well over a year now. Their original white paper, and all these are linked, dates back to, I think, April of last year, where they basically laid it out bare. The infrastructure bottleneck for AI, the bottleneck towards accomplishing all of our goals with AI, comes down to memory. It's that simple. Memory, unlike GPUs, unlike the LLMs themselves, unlike the context windows that keep growing, we're at the 1 million+ Sage tokens right now with Llama 4 is mainstream and Google's had it for a while. Memory is just not kept up with Moore's law. And so it's all about figuring out intelligent ways to maximize and optimize the memory we have. There's a trend right now. In fact, I like to joke, the formula to actually making money in AI is XYPD. What does XYPD stands for? It stands for how much prefill can you minimize? How low can X go? how few times are you going to have to pre-fill the same key value matrix from the same token prompts? Think AI agents, think 16 prompts, think up to 16K, 16,000, maybe 20,000 tokens per system prompt before your prompt gets added, before your content gets added. How few times how few times can you avoid redundantly pre-filling that? So you can actually devote your precious GPUs, GPU cycles, GPU clusters on the decode part. That's what we actually pay for. That's what we want. And so there's a KV cache, key value cache, that's emerged there. And there's a very, very elaborate hierarchy that NVIDIA now has documented that extends beyond merely memory all the way down to storage. But it's a trap. When you actually do the math, and very few companies have actually done the math here, and certainly even fewer have publicly disclosed them. I say this because, of course, WEKA is one that's done the math and disclosed this. You'll see that it isn't a very simple, elegant hierarchy that's drawn here. There's actually quite a big cliff between, as you can expect, between the performance of memory and the performance of storage, even flash storage, even NVMe. And this whole geeky industry term you might have heard before, NVMe, what does it stand for? It actually stands for non-volatile memory extension. And what we're about to see is AI inference is probably the first mainstream application that really pushes NVMe to not act like disk or solid-state disk or flash drive. It really forces NVMe to act exactly like what it's named, a non-volatile memory extension. So what really is comprised of that? Well, you look at the classic AI triad. Any researcher knows this. A lot of infrastructure operators know this. You've got your accuracy. You're always trading off accuracy, and at the end of the day, it's the number one priority. I'm not interested in a partial answer when I prompt ChatGPT or my favorite LLM, especially through an API. I'm interested in the best answer. And the best answer always comes at a high cost. So there's always a trade-off between accuracy and cost. And the biggest lever we have is latency. Not just in terms of the latency of getting the response back to the user or the response back to the agent, the API, but that infrastructure latency, which lets you make much better trade-offs. And these triads are always making trade-offs, much better trade-offs between accuracy and cost. So you don't have to sacrifice as much accuracy to still be in the cash flow positive business, the positive unit economics of AI inference. And good things happen. When you reduce latency, you've got this nice clockwise, elegant, directed graph happening, where you're essentially delivering more training or more inference cycles per fixed budget. Power is a hard limit. Rack unit space is a hard limit. The actual flops and the memory bandwidth utilization of a GPU is a hard limit. The NVLink networks are hard limits. So it's all about how many more cycles can you generate per all those hard limits. And being able to process cycles at a lower latency is what actually delivers, all of the good things we want in terms of more tokens, more accuracy at that lower cost. And so just to paint the obvious picture, when you have high latency, and this is a trap, again, people fall into because people think, well, if I buy the highest bandwidth storage, because bandwidth is good, right? Memory bandwidth is important, that's true. Storage bandwidth is important, that's true. But if it comes at the cost of high latency, you lose all these advantages. And you end up with basically not just inefficient infrastructure, a horrible user experience, really no traction in your service, and it all tends to go downhill. It's really a worse practice. So how does this map to numbers? One of my favorite firms, the new Gideon Gartner, if you know the analyst racket, is a guy called Dylan Patel. And Dylan Patel is very charismatic. He does a lot of YouTubes. He gets invited to all the coolest podcasts nowadays, including Lex Friedman, if you haven't seen his epic 5-hour podcast, along with Nathan Lambert. And I tried. I literally was the only Lex Friedman podcast that I consumed live for the entire 5 hours without a break, and I did fall asleep at the end. But the good news is their editing team created amazing 5-minute, 2-minute, 30-second clips of that 5-hour podcast, and they are gold. And one of the golden, elements of this is a report that Dylan wrote with one of his co-creators, his colleague actually, Dan Nishbal. Dan's out in Singapore in their Singapore office. Dylan's over here now. And this is an old report. It's almost 2 years old now, 18 months old, from October 23, called A Race to the Bottom. I highly recommend, if you care anything about the business of AI and the token economics and unit economics, to read this report, because it lays it out bare. And it basically points to the fact that if you can't process more queries, prompts per cycle, and I'll detail exactly what those look like, you're just not making money, you're losing money. And a couple of major recommendations of this report, which Jensen loves, by the way, is that you have to be on the latest processors to be able to generate the tokens per second, or if you want to measure it as tokens per hour, that you need. You have to be able to have enough memory to run as many simultaneous user sessions as possible. That's the batch size. And it's a thin, thin line in the business of inference. So people that will be around next year from a model providing and GPU providing perspective, it's a thin line between the red and the green, the loss and the profit. So it really does come down to performance, and it really does come down to the latency of your infrastructure. So let's just visualize this. What does this really mean? Inference fundamentally is a sine wave. So you've got amplitude at the beginning, which is a GPU and a memory. And whether it's model loading, whether it's prompt processing, whether it's pre-filling and decoding, those large system prompts that we have right now, particularly in the agentic systems, you've got the top part of the amplitude there. And there still is a role for storage. It's a bit existential, but if you have RAG, retrieval augmented generation, then you've got to optimize the embedding performance, and you've got to certainly optimize the retrieval performance, because you typically don't just do one retrieval in an enterprise AI, enterprise RAG context. In agentic systems with quality, with judging models, with guardrail models, you're doing dozens, perhaps hundreds, if you really want high quality, of retrievals, and your latency budget is still fixed. Your user is not going to wait that much longer. Your infrastructure can't wait to just service one user when there's 100 others in the queue. So again, it all comes back to latency. And naturally, the more you can compress the wavelengths, why is 5G Wi-Fi here faster than 2.4G? Why are 5G mobile networks faster than 3G and 4G, the prior generations? It's the wavelength, stupid. It's more data per budget, per time slice. That's what it comes down to. And this is fundamentally what you want, in your infrastructure. So let's revisit now the ARC prize. Now we're at ARC AGI-2, and they've wised up because they've realized that I think the original estimates were about $1.2 million for O3 when it came out in December. We didn't have O3 mini, O3 high, it was just O3 preview back then. So about $1.2 million of processing for 16 hours. And that's how they defeated the ARC Prize 1 benchmark. So the ARC Prize team said, okay, we're onto this for ARC Prize, ARC AGI-2. We're going to bake efficiency into the benchmark. So you can't cheat and just throw infinite compute, infinite resources at a problem. It's still impressive that you can do PhD level Nobel Prize winning things. So you do have artificial PhD laureates, Nobel Prize laureates at your disposal, but we're in the real world here. In the real world, we have to combine model research. We have to optimize our infrastructure. And if we want to be around next year, literally, because the VC cash is kind of running out, revenue is a really important thing right now. It's what's going to keep the positive cash flow going. We have to optimize our token unit economics. And when we do that all together, magic happens, as we saw this morning in the morning keynote, the AI, in the Women in AI talk, where we saw Lynn from MSK, the Cancer Research Center, talk about new cancer treatments, AI-powered, that have a 100% success rate. All 42 patients in this new treatment are in remission. These are amazing results. These are what good AI infrastructure delivers. And I urge you to follow us and reach out if you want to find out more about how we literally are changing the world together. Thank you for your time.